My name is Craig, and this is my presentation on comparisons of various methods of precipitation measurement and estimation. First, I'll take you through a little background of the NC EcoNet. It is a mesonet maintained by the State Climate Office of North Carolina. It is an automated network that measures environmental variables such as wind speed, solar radiation, precipitation, etc. at various levels. A little background on the instruments that they use. The NC EcoNet currently uses the tipping bucket gauge and an impact sensor, while the ASOS stations use a little bit more of a high-tech tipping bucket gauge. Various other networks in North Carolina use various different types of gauges, but generally they all use tipping bucket gauges. Now onto multi-sensor precipitation estimates, or MPE. This estimates precipitation using both radar and ground gauge data. It also uses a local bias adjustment with co-op observations to correct the precipitation field. MPE is gridded at a 4.75 approximately resolution, computed hourly. Radar is susceptible to various sources of error, including bright banding, hail contamination, and then most importantly range degradation. Ground observations are susceptible to other sources of error, such as partial or full clogging and sampling errors. All data in this study is daily from 12Z to 12Z and is quality controlled. The primary motivation of this study is that the North Carolina State Climate Office is currently implementing quality control procedures based on inter-sensor comparisons with gauge and impact sensors, and then also a loose comparison with MPE. The research questions for this study are: how do the gauge and impact sensors perform relative to each other and other networks within the area? How do these compare with MPE? What effect does quality control have on correlation between the EcoNet observations and MPE? The study site for this was North Carolina, and the study was broken down into 3 separate precipitation events. Case 1, which was Hurricane Irene, which is primarily an East Coast precipitation event, extremely heavy, extremely localized, and it dropped off the farther you get inland. Case 2, which was a more of a frontal passage with stratiform precipitation, primarily on the moderate to heavy side, and then Case 3, which was a little bit more isolated and on the lighter side overall, precipitation-wise. Only the methodology and results from Case 1 will be explained in this presentation. The results from the other cases can be seen at the full paper at the link provided. Here's a quick radar animation obtained from weatherunderground.com of Hurricane Irene for Case 1. As you can see, it's primarily confined to the East Coast. And here's Case 2. And here's Case 3, the frontal passage. All observation data is obtained from the State Climate Office of North Carolina's Kronos database. All data is obtained from 12Z to 12Z to coincide with MPE. Hourly and daily data are obtained from the start of the period to 1 full day after the end of the event in order to resolve any reporting differences between networks. And this works because all of these events were discrete. They had a beginning and end. There's no small precipitation amounts in the in-between periods. MPE is obtained from the Advanced Hydrologic Prediction Service, and all data is in WGS 1984 Geographic Coordinate System with WGS 1984 data. All data is projected to decimal degrees. And on to the methods and results. For each case, all these methods were applied, but the results that you see here are for Case 1, Hurricane Irene. So for this case, splines with tension and kriging methods were compared and then analyzed through use of cross-validation and root mean square error comparison. And as you can see here, overall, spline with tension performed worse in terms of root mean squared error compared to kriging. After the best interpolation method was determined, the precipitation fields were interpolated. So for case 1, kriging was used. And here we can see the Equinet gauge plus all other observations in North Carolina and the interpolated field from that for Hurricane Irene. And as you can see, there's a core of about 9 to 10 inches of precipitation right in the eastern North Carolina region. Here we can see MPE for this event. As you can see that there is a core right here in the white area of over 20 inches of precipitation occurring in this area according to MPE. And then in this purple zone, you see anywhere from 14 to 20 inches of precipitation. So overall, much different than the other networks observations, including the gauge. Next, cross-validation of the interpolated fields and MPE with observations was performed. In this, you can see red values here are where the observations are less than MPE. So in that eastern region, there is something like a 7.5 to 15 inch difference between MPE and all of the observations in North Carolina. Linear regression was then performed using surface observations and MPE. Correlation between Equinet, other networks, and MPE were identified. Proposed quality control procedures were then applied and correlation coefficient was reevaluated. And here you can see the linear regression before quality control. So for Equinet impact sensor with all other networks data included, the R-squared value is 0.6507. But when you include the gauge instead, the R-squared value is 0.5824. And then the gauge compared to MPE is 0.547 about. And then the impact sensor in the MP, it's 0.8128. So in this case, the impact sensor correlated much better with MPE. However, after quality control was applied, the gauge correlated much better with MPE as opposed to the impact sensor. Subregions within the zones of light, moderate, and heavy precipitation were chosen. These were then analyzed using cross-validation with only observations within these regions included. So the figure here shows select observation sites where precipitation was greater than 5 inches indicated by MPE. As we can see from the table, the difference between the other network's observations and Equinet impact sensors was an average of negative 0.609 inches, meaning that the impact sensor was much greater than the other network's observations within the region. Conversely, the Equinet gauge was much closer to the other network's observation at a negative 1.06 inches difference between the other network's observations and Equinet gauge, where also the difference between the MPE and the Equinet impact sensor was negative 1.96, and the difference between the MPE and the Equinet gauge was 2.84 inches, and the difference between MPE and the other network's observations within the region was 2.51 inches. So essentially, the Equinet impact sensor was much closer to MPE, whereas the Equinet gauge was much closer to other networks observations within the region for heavy precipitation. So kind of a summary so far, kriging was determined to be the most appropriate method of interpolation for case 1. The results for case 1 show that for the region of heaviest precipitation, the Equinet impact sensor was the closest to MPE, whereas the Equinet gauge was much closer to other network gauges within the region. This is likely due to other networks in the region also having gauge clogging issues during this event, just as the Equinet gauges incurred. The distinct advantage of the impact sensor is the fact that it can't clog. Thus, for other non-quality control data, the impact sensor appears to be much more accurate compared to the gauge for this area of extremely heavy precipitation. For moderate and light precipitation, the Equinet gauge was much closer to MPE and the surrounding network's observations. In those cases, those breakdowns can be seen in my paper. what still needs to be done. More cases. The sample size of this study is too small to make definitive statements with real accuracy, and quality control of all data outside of Econet and MPE is not quite as great as it is for Econet and MPE, and some of the data is not even quality controlled. So in conclusion, in higher precipitation, the difference between MPE, Econet gauges, impact sensors, and MPE increase. For uniform precipitation events, the overall differences between these increase with greater precipitation, but the percent difference relative to MPE does not. Quality control of the gauge and the impact sensor, removing flagged values from the regressions, improves the correlation of gauge and impact sensor with MPE. MPE also may have a higher degree of error in very light precipitation events as opposed to moderate or heavy precipitation events. So that is relative to the Econet gauge and impact sensor and other networked gauges. In moderate precipitation, there is less difference between the Econet gauge and other networks data and MPE. And those are my references. Thank you for your time. That will conclude my presentation.